Okay, I've made a couple of little revisions. Now, I want to talk about the area of this typical ring. Okay, remember it's a ring of a small width delta r, a radius r, where r is a representative radius somewhere within the ring. And we're going to ultimately want to find the mass of the styrofoam within this little ring. Since r doesn't vary much, once we have that mass, we can just use the product of mass times r squared to get our contribution to the moment, our approximate contribution to the moment of inertia. So that's kind of where we're going with this. Well, if our density is in units of mass per unit area, then we would just multiply that density by the area of the ring to get the result. Now, people, when I asked them to calculate this, not everybody got a calculation, but most people who did subtracted an outer, subtracted the area of the circle inside the ring from the area of the circle from the outside of the ring. Okay, so you got a circle here minus a circle here. That's okay, but that's overkill because we're going to be taking a limit after all as our delta r approaches 0. So what we can actually do is we can just say, well, if I've got this thing, its circumference is 2 pi r. So I can say that the ring area is approximately equal to its circumference times its width. Why is that? Well, if you imagine cutting this thing right here and unraveling it, how long is it? Its length is equal to the circumference. And how wide is it? Well, the width is your delta r, the width of the ring. And that result then is circumference is 2 pi r, where r is your representative position, okay, your representative distance from the axis of rotation times delta r. Okay, so if mass is area times density, the mass of the ring of radius r and width delta r is what? Well, it's just going to be this times your density. 2 pi r delta r is your area. And if we multiply that by your density rho, and rho is usually a volume density. I probably should have used sigma here. But we're just going to understand that rho is the density of the styrofoam in units of mass per unit of area. So we get this expression then for the ith interval. Now I've skipped the whole thing about partitioning r from 0 out to whatever the outer radius is, but we should pretty well understand that by this point. So the area will be 2 pi r sub I times delta r sub I, and I usually use an asterisk to indicate this representative distance, and the delta r sub I doesn't have a star on it. So following pretty well standard calculus procedures, we sum up the areas over n, say, different rings that extend from here to here. We partition the circle into concentric rings. We add up all the moments of inertia of the rings. We add up, in this case, well, actually we're just calculating the mass here, okay, not calculating moment of inertia. So, again, this sum approaches the integral of r with respect to r. And the integral goes, it's a definite integral, goes from the radius of a point the R value for point at the center, which is 0, to the R value for point out here, which is A, radius of the circle. So we have this integral, it gives us this result, and this is going to be our mass. So total mass is approximately equal to this sum, and we get this mass. Now, if we wanted to get the moment of inertia, and it doesn't look like I've done that here. I thought I had, but I didn't. The moment of inertia is the moment of inertia of this little bit of mass would be the mass of a typical ring. You would just multiply that by the square of R, because it's mass times R squared. Moment of inertia, you add up all your masses times R squared. So your moment of inertia integral would end up being 2 pi rho times the integral from 0 to A of, well, if you just integrate R with respect to R, you get the total mass. If you multiply this by the R squared, you're going to have an R cubed here. You'd have an RI squared up here and so forth. So you'd have R cubed dr. And antiderivative is going to be R to the 4th over 4. At the limit, you're going to get an A to the 4th over 4. You're going to get a 2 pi rho A to the 4th over 4. I can tell you then that if this is the mass, then how could you express I in terms of the mass? Well, you've got a 2 pi rho here, you've got a 1/2 here, and you've got a 1/2 here, and wait, that shouldn't have a 1/2 pi. If I use these two expressions, well, let's see. I should be equal to 1/2 m A squared. Okay, but if we multiply this by 1/2, we get pi over 4 times that, and then times A squared gives us the A to the 4th. Something's wrong here, so I'm going to have to somehow reconcile that. I don't see anything here. All these steps are very simple. I don't see what's wrong, but I need to fix this, so I'll be back with a brief correction here.